All right, y'all. Today's lesson, we just got to review a little bit from yesterday, just to remind you of a few things. And then we will work on multiplying with complex numbers. So yesterday we introduced the imaginary number I. And I've got that down here in green, where the imaginary number I, again, not we call it the imaginary number, but it's as real as any other thing. It has to be used in mathematics to keep track of the square root of -1. So it's just a direct substitution. Where you see an I is equal to the square root of -1. Or if you see the square root of -1, it equals I. And then the other thing, we didn't use this yesterday, but we will be using it today, that by definition, I squared is equal to a -1. So anytime you see I squared, you can actually change it back into this really a real number, -1. The other thing I want to point out is remember these complex numbers have two parts. They have a real part A and the imaginary part B. Okay, so it's got two parts to it. Not all numbers show both those parts. Um, we talked about it a little bit yesterday. Every single number you've ever used, like the number 3, we never show the imaginary part to it because it is 0 imaginary part. So we never showed this. And then we had pure imaginary numbers that were like 5i, where they didn't show the real part. It's because the real part's just the 0, so we just don't show that. And so this would be pure imaginary. And we learned today, and hopefully practiced it in our homework, that we could add and subtract complex numbers. Okay, so I have a complex number here, 4 plus 5i, and I want to add it to another complex number, 6 plus 2i. And so to add them, we always just add the real parts together. So 4 plus 6, that would give us 10. And then we add the imaginary parts together. We got 5i plus 2i's. It's like saying I got 5 root -1s plus 2 root -1s. How many root -1s do I have? And that would be a total of 7. 2 plus 5 or 5 plus 2. And that's where we stop. I can't combine a 10 plus a 7 root -1 or a 7i. And it's so much easier to say 7i than it is to keep referring to it as a root -1. Okay, here's a subtraction problem. And so to subtract these, we do have to do some distributing here. 4 plus 5i doesn't really need parentheses around it, but I want the opposite of all these. So I distribute, think of this as a -1 I'm distributing. So -1 times 6, -6, and -1 times 2, -2, and then my I. And then I do what I did in the first problem. I add the real parts together. In this case, it's a 4 minus 6, so it's -2. And then I add the imaginary parts. So 5i, take away 2 i's, gives me a total of 3 i's. And I stop right there. And I've added or subtracted, in this case, two complex numbers. Today's all we're doing is multiplying. Now, the nice thing about multiplying is that we can always do it. Now, I just want to remind you, like if I had 3 times 2x plus 4, I have to distribute that 3. And I get 3 times 2, 6x, and 3 times 4, 12. And I stop because these are not like terms. I cannot combine those. And so we do the same thing with complex numbers. Here I'm just multiplying 2i, a pure imaginary, times a 3i. Now, when we see that 2i and that 3i, this really means 2 times I and a times a 3 times an I. Everything's just multiplied together, and we can multiply in any order. Okay, so what we're really doing here is the 2 times 3 part and the I times the I part. Now, you don't have to write all of that out when you do this. Think of it like when you do like 2x times 3x, you get 6, the 2 times 3, and the x times x is x squared. So the same thing happens when we deal with complex numbers. We do the 2 times 3, which gives us the 6, and the I times I gives us I squared. But this is where that second part of the definition of the imaginary I comes into play. Remember, I equals square root negative 1, but also I squared is equal to a negative 1. And that means we can do a direct substitution right here. I squared, well, that's the same thing as negative 1, so this becomes 6 times negative 1. It becomes a negative 6. The same problem is written over here to the right, but I just wanted to show you it with parentheses. Okay, this isn't distributing. Okay, we're not distributing multiplication over some addition problem. This is just multiplying 2i times 3i, so we get the same thing. 6i squared. I squared is negative 1. So 6 times negative 1. Okay, just a different format for a multiplication, but sometimes we get confused about that. Let's do one where we do get to do some distributing. Here we go. We got a 2i multiplied by this complex number, 4 plus 5i, so we have to distribute. So we do 2i times 4. We just multiply the 2 and the 4. That's 8, and then we got our times the I. Then we go plus, because it's a positive 2 times a positive 5, so 2 times 5 is 10. We get an I times I, which is I squared. But remember, I squared is equal to negative 1, so it's 10 times negative 1, so it's 8i, and 10 times negative 1 is negative 10. Now this is a correct answer, it's just not written in standard complex form, which is the real part first. So our real part is the negative 10, and our imaginary part is the 8i. So that is our best form for the final solution. Same type of problem. This time I'm distributing though a negative 3i, because I think sometimes negatives goof us up a little bit. So we have a negative times a negative, that's going to be a positive. A 3 times 6, that's an 18. And then that times I, so 18i. We've got a negative times a negative, so that's a positive. Then the 3 times 4, that's a 12. And then the I times I, which is an I squared. Now, in general, we don't show, you can show it. So like 18i plus 12 times, well, I squared is negative 1. So it's 12 times negative 1, which is minus 12. And then we put the real part first, the negative 12, and the imaginary part second. But in general, the workflow looks like this. You just jump from this statement above to this guy. Oops, we just go, oh, that's going to be a negative 12. And then we can put the real part first. So you don't have to show that substitution. If it makes you more comfortable showing it, that's just perfectly fine. But just know I squared is negative 1, so it's always going to change that sign. I squared is negative 1, so we'll just change this sign every single time. If this was a plus, so it changed it to minus. If this was a minus, it would have changed it to a positive. Next example here. Now we have a binomial times a binomial method of multiplying these two complex numbers. Okay, so here we go. We got to take the 2 and we distribute. So 2 times 4 is 8, and 2 times 5 is 10, and then times the I. Then we distribute 3i. 3i times 4 is 3 times 4, 12i. And 3i times 5i is 15, and then we get the I squared because you have that I times I. So let's clean things up a bit. We got our 8. These are both imaginary terms. I got 10 i's plus 12 i's, so that gives me a total of 22 i's. And then this is the one that always gets people. They forget this part here. See that I squared? So this is really a 15 times a negative 1, because I squared is negative 1, so that becomes a negative 15. And that gives us another pair of like terms. 8 and negative 15 are both constants, just numbers. 8 minus 15, that's negative 7. Then our imaginary part, 22i. We have this nice complex number, all simplified, and we are done. Last example, very similar to it, but I want you to see one with some minus signs inside of the two complex numbers. So let's distribute this 2. 2 times 5 is 10. 2 times negative 6i is negative 12i. Distribute negative 3i, that's negative 15. Negative 3 times 5i. And then distribute it here. So we get a negative times a negative, that's going to be a positive. 3 times 6 is 18, and I times I is I squared. We got some light complex or imaginary numbers there. It's negative 27 i's. Here we got that I squared, so it's 18 times negative 1. It's minus 18, and that means we can combine these two real numbers. 10 minus 18 is negative 8 minus 27i. And we are done. So your problems today are just multiplying using complex numbers and get it to the simplest complex number that you can get to. And that's it. Pretty short video. And we'll solve equations involving the complex number tomorrow, or Thursday, I guess.